I'll be talking about warehouse scale computing. In particular, I'll talk about this new project we're starting at Berkeley called FireBox, which is looking at what should a warehouse scale computer look like in 2020. And this is a project I'm working on jointly with David Patterson inside the Spire Lab. So I've been looking out at what are these future applications everybody wants to do. As architects, always look ahead and see what do people want to do. And there's a whole range of exotic new applications people are thinking of all across the space. People want to have augmented reality, speech interfaces to agents, crunch huge amounts of data, troll through social networks, sense things in the environment. So there's all these new applications people are coming up with. And if you look inside and see how people are imagining these things will be running, you see there's this migration of computing to the extremes. Basically, small devices, mobile phones, Internet of Things, out of the environment, collecting data and sending it back to the cloud, which is this large-scale computing infrastructure that's been built up. And what you'll see is that most of those mobile and Internet of Things types of applications, they're increasingly being supported by the cloud in the background. And basically, all data is being backed up in the cloud. And there's this ongoing demand to support this huge upswing in computing for ever larger, ever more powerful warehouse scale computers. And when we started looking at this, we sort of tried to figure out what's been happening in this warehouse scale computer design space. And we sort of divided the world into recent history into three warehouse scale computer generations. So the first generation is really turn of the century warehouse scale computers. How were they built? Well, basically, you would go to catalogs and buy off-the-shelf servers, maybe from HP Dell, and switches from Cisco, wire them up together to build your warehouse scale system. So the last decade or so, people started moving from just buying off-the-shelf systems to increasingly building their own custom designs, custom computers, custom switches. But mostly, these are just board designs reusing off-the-shelf chips from vendors like Intel, for example. So looking ahead, what we see is in the third generation are going to be much more customized computers for the warehouse scale, including designing custom chips designed purely for the warehouse scale. And so another couple of trends I'll talk about today is this moves from a horizontal organization of the systems where you have, for example, Linux on top of x86, to more vertical integration of the various service providers, where they're going to have their own whatever warehouse scale operating system they think is appropriate on top of the kinds of chips they think are appropriate to run that kind of workload. So move from a horizontal model to a more vertical model in the architecture of these warehouse scale computers. Another thing I want to talk about is the increasing impact of open source across these generations, from software to hardware, how open source is affecting things. So just want to present the talk outline. So most of the talk, I want to go through the warehouse scale trends and challenges as we see them. And these are sort of the background we did looking ahead to see what should be doing in warehouse scale computing. I'm going to cover things like programming productivity, tail latency, memory hierarchy, security, technology scaling, and this trend towards open source hardware. Then I want to describe FireBox, which is really our vision of putting this all together. What do we imagine the future warehouse scale computer is going to look like in 2020? And just to give you a sort of sneak preview of our answer there is, the server of the 2020 warehouse scale computer is going to have about 1,000 sockets and 100 petabytes non-volatile memory connected by an immense switch, 4 petabyte per second switch. This is a system that we actually want to prototype in a few years. So I'll let you know how we imagine doing that. And finally, I want to touch upon a very important problem is we want to build this large-scale system, but we want to understand all the design trade-offs. So how do you simulate a warehouse scale computer? I'll talk about a project we've done at Berkeley called Diablo briefly at the end and show you results from a system that can simulate basically most of a data center, executing every instruction and watching every packet and every byte go by. Okay, so let's dive in. How do people program these warehouse scale computers? So let's start at the top. So there's been a massive trend towards what we call a service-oriented architecture. If you're not familiar with this, the basic idea is every software component should be designed as a service. Basically, that means it's an abstract data type. There's a bunch of data hidden inside there, but you can only get at that data through very well-defined interface, methods on that data. And you only communicate with these components via the network. You message to a service that provides some operation on the database inside there, returns some values to you, but all over the network. So quite isolated components. And an application now is composed of a whole gang of these interoperable services working together. And the nice thing about this, it's easier to play with these designs. It's more modular. You can reuse these components more easily. And if you contrast this to a sort of traditional sort of silo model where you start off with a specification for a whole application, write the whole thing monolithically, the advantage of the service-oriented architecture should be clear. You can have these reusable modules. So just to give you an example, I'm using a little example from Dave Patterson's and Mondo Fox's book on software engineering. This is an example of a bookstore designed as a silo. So for example, you want to provide this bookstore service. You may internally have a few different data structures. You write this with API, and for example, one component can interrogate directly the data of another piece, because that's kind of convenient and easy to do, and there you have your single app. But if you were to design this using the service-oriented architecture, you break this up into separate modules, and these subsystems can be truly independent. They could run in different data centers, and each of them, you communicate via the network to them. You send messages to have the services performed. So data is sort of encapsulated inside each of the service and only accessed through the interfaces. And it's quite easy to recombine these to make new services. So this is kind of the approach people are taking. So why are people doing things this way? Why are they modularizing things, encapsulating things, adding this sort of overhead of communicating via messages? Well, one reason is just it's a successful way of building software. If one thing we've learned about building software is trying to build a very large piece of software, it doesn't work. And I have some data here from a recent study on looking at, I think, 50,000 software IT projects and cataloging the size of the project and how successful they were. So small projects we can do reasonably well at. So small projects are sort of $1 million scale. And the data there is about 3/4 of the time they succeed, they're on time, they provide the functionality you asked for. However, 20% of the time, you're going to be missing some functionality, or it's going to be late. And occasionally, 5% of the time, you're going to cancel the project completely and just throw away the investment in that project. So that's a small-sized project, and that's not too bad. However, if you look at large-scale projects, so up $10 million and up, the picture is very different. So here, basically, half of the projects are late, missing functionality, and nearly 40% of the projects are just canceled, just thrown away. So these are very large projects where 40% of the time you're basically throwing away the entire investment you made in that software. So the message from here is we can manage small-scale chunks of software development. We cannot manage very large-scale pieces of software development. And you kind of feel sorry for President Obama, who was trying to push through the healthcare system. If he'd seen this data, he would have known there was no way at all that it would be possible to get the system deployed using this monolithic approach, which unfortunately the government procurement process required them to follow in pushing through that Healthcare Act, right? So small services are the way you want to build large-scale systems because it's easy to get each one built individually. The two-pizza team, as Amazon calls it. So talking about Amazon, just share an anecdote. So accidentally, an employee at Google ranted on a blog that he thought was internal about Google's not adopting this model compared to how Amazon had adopted the model. And he shared this story about an email they received at Amazon from Jeff Bezos. Now, this was about in 2002, 7 years after Amazon had started. And basically, the CEO declares all teams will henceforth expose their data and functionality through service interfaces. Teams must communicate with each other through these interfaces. There'll be no other forms of inter-process communication allowed, no direct linking, no direct memory, no direct access of each other data structure, no shared memory model, no backdoors whatsoever, right? So he's laying down the law here. And furthermore, these service interfaces must be designed to be externalizable, i.e. they're well-defined enough you could give them to an outside developer to connect to, right? And so this is quite an edict coming down from the CEO. So how does a CEO make sure his company follows this model? Well, it's pretty simple. Anyone who doesn't do this will be fired, right? So this is email from Jeff Bezos. So service-oriented architecture is how you want to structure these big warehouse-scale applications. So now looking at trends and challenges, I want to go through a bunch of, I'll structure this as old versus new conventional wisdom to see how things are changing out there in the technology industry. So the first one I want to look at is this idea of fault tolerance being critical. So the old conventional wisdom is that fault tolerance is critical for a warehouse-scale computer. You have to be able to successfully complete a function even if some of the parts fail. So you want to build reliable systems from less reliable parts. So that's still kind of true, except the new conventional wisdom is not only that, but you have to have tail tolerance. A lot of the applications people want are latency sensitive. They're user-facing. Requirements are to respond in hundreds of milliseconds or less. So the new requirement is that if slow is failure, you have to build predictable response from components whose response may be unpredictable, right? So how do you make a predictable whole system when individual pieces may perform less than ideally? So this comes from, so looking at it this way, it comes from a paper from Jeff Dean and Luis Barroso at Google, a recent one in CACM. I just want to highlight some data from there. So they take an example of a Google service where a request comes in, that request then gets fanned out to a bunch of other servers. The initial request has to wait for the responses to come back before they can respond back to the original requester, okay? So you have this sort of fan out of sending little messages around the system and pulling that all together. So as a computer architect, I'm kind of used to looking at average case performance as our metric. And if you look at average case performance in this case, it's like around a millisecond on average for some response to come back in the system, one of those requests that you send out. However, if you're interested in the tail, if you go further out and say, how long does it take for all the requests to come back for 99% and the 99 percentile case, it's 2 orders of magnitude worse, 140 milliseconds. And in fact, waiting for the last few percent of the request to come back can double your experience latency, right? So in order to provide the responsive services, you have to deal with this effect. You can't just design for the average, you have to design for the tail. So the old conventional wisdom is the main cost metric for building hardware is cost performance and average energy performance. But now we have to build the hardware to provide this tail tolerance, right? So it has to be energy performance given this tail tolerant behavior. Oh yeah, so Dave loves cars. So a lot of the cars on here from Dave Patterson, and some of you may know this, these are both Cobras. Right? Okay. So how are we going to do tail tolerance? What are the things we can do? Well, in software, some of the things mentioned in the paper, basically dividing up the applications into different service classes. So don't have a high priority request queuing up behind a lower priority request. Try and differentiate the queues there. When you have a long running request that might occupy a resource for a long time, break that up into smaller pieces so you lower the latency of something else getting in there. Another thing is actually actively programming to cope with the variability. So in this paper, they outline a couple of techniques. One is hedged requests, where you send a request, a few milliseconds later, if you haven't heard anything, you send a request somewhere else and hope to get that answer back. And you wait a little so you don't always duplicate all the work. It's only in the cases where something is slow in responding. Another thing you can do is send requests to 2 places and queue them up in 2 different queues. When the first one is serviced, you actually send a message over to the other queue saying, don't worry, I have it handled over here. Right? So you're hedging your bets by queuing up in 2 places. Now, in the hardware, there's a bunch of things we can do. One thing is any distributed systems, basically the network always seems to be the bottleneck when you're breaking things up. So provide a faster network is something hardware can do. That'll reduce queuing. Also reduce the per message overhead. What you see now is as you're trying to cope with tail tolerance, you're generating, you want to break things into smaller pieces and have more messages between them. And you're sending more messages around to provide redundancy. So you want to reduce the per message overhead to help with all these techniques the software is using. And finally, another thing we need to do in the hardware is be better at partitioning these resources. We're very good at sharing resources, putting lots of cores on a chip and sharing DRAM channels. But when we have different applications level services, what we'd like to do is be able to partition that off so we can guarantee bandwidth for tasks that we consider latency critical, and perhaps retaining high utilization by letting the background tasks fill in when that high priority task isn't using. And this really is not something that can be done by software alone. So we need hardware help to help provide mechanisms to partition hardware resources. Okay, so this is a storage technology conference, so let's talk about what's happening in the memory hierarchy. So the memory hierarchy, for as long as I've been involved in computer architecture, has basically consisted of these 3 levels. You had DRAM, disk, and then tape as archival storage, cold storage off to the side. And Jim Gray, a while ago, sort of pointed out, well, really, this is changing. This is going to change. And tape is dead or receding, and disk is the new tape. It's the cold storage. And flash is the new disk. And one little caveat here is, as an architect, what I see happening is the DRAM is now moving, the fast DRAM is moving closer to the processor. So we have this new tier of very high bandwidth DRAM. The bulk memory is probably going to become non-volatile. And disks are sort of receding off to be the cold storage in these new systems. So let's take a look at non-volatile memory. I know it's a hot topic here at this conference. Well, the old conventional wisdom is that 2D flash, two-dimensional flash, is going to keep scaling at Moore's law. And that's basically pretty much over. So, so the way this technology is going to go forward is either 3D flash or some new non-volatile successor. And there are a lot of candidate technologies out there to replace flash. I'll just list some of the more popular ones. And all of these ones have the property that they get closer to DRAM in read latency. Flash is really slow. And they tend to have better write endurance than flash. So examples are resistive RAM, spin transfer torque, magnetic RAM, or phase change memory. These are all candidates that are playing out there. Who knows which one of these will actually come through, but it's likely or is needed that something will be there to take over from flash, because flash is kind of slow and it's not scaling very well, and the 3D flash is just coming on the market. Maybe that's it, but it's going to be pretty slow as a non-volatile memory. So I've been looking at analyzing this, and you can build these sort of spider charts, looking at different properties of which one has better write endurance or cost per bit over time. And this is a battle that's ongoing. But in this project, we're just assuming that something is going to happen to give us much better non-volatile memory in the future. So if we take a look at what that implies in system design, I'm borrowing this slide from one of our collaborators, Bob Brennan at Samsung. If you sort of look back at the conventional sort of 2010 era memory hierarchy, you have this traditional DRAM, disk, tape. What we're seeing happening now is more levels appearing in this storage hierarchy. So DRAM itself is bifurcating into the high bandwidth DRAM that lives on the package close to the processor, and bulk DRAM, which provides high capacity but out on the motherboards. So that's one extra level. Also, we're seeing the disk level sort of breaking into solid-state drives using flash, and traditional rotating disks providing large-scale code storage and archival storage. Now, looking ahead to 2020, how do we see this changing? Well, one thing that might happen, if we have a reasonable flash successor, we'll see that flash being sort of considered along with the DRAM as part of the bulk memory of the system rather than hiding behind a disk interface, right? Sort of move towards a more PCIe or even closer connection of the flash, of the NVM. But if this new NVM successor actually takes off, this whole tier of bulk DRAM plus bulk NVM, we can see that potentially merging and the system simplifying to now where you have just this one tier of very high performance bulk non-volatile memory out there. And the DRAM in the system is really this very high speed buffer very close to the processor. And disks are sort of receding off into the, the sunset as the archival code storage in these big systems. So this lens, this is one of the really key driving technologies for these new data centers. And basically, what we're seeing is what we believe will happen is we'll move towards a solid-state data center. That's what's going to be happening as the advances in these technologies. So what about security? Very important. As more applications, more businesses, more consumers, medical records, everything moves into the cloud, people worry about security. And I think a few years ago, when we were talking about these ideas, the conventional wisdom we perceived at lots of places was that you really just need security at the borders of these warehouse-scale computers. Don't really worry about it inside the warehouse-scale computer. Well, if you've been watching the news, a lot of recent events, force people to change their minds about this. And I think the new conventional wisdom is that given that, foreign governments, industrial espionage, even our own government are spying on us, but also the amount of damage that a single disgruntled employee inside your organization can do requires that all the data, all the time, is maintained encrypted, right? So across the network, inside the warehouse-scale computer, in the NVM, it's going to be encrypted all the time, right? So no clear text data stored anywhere at all. This is the new world, the new reality we're going to have to be living with. So now, this is obviously going to impose some more demands on the computing. What about our old friend Moore's law? So let's now talk about logic and memory, other kinds of scaling. Well, the old conventional wisdom was Moore's law. Technology generations every 18 months, you get better transistors, performance and energy improves, and the cost per transistor drops down as you go to each technology generation. Smaller transistors, bigger wafers. Well, the new conventional wisdom is this has really slowed down. Like the last few years, been tracking technology changes. The next node, 14 nanometer, is that there and sort of ready to go, except nobody wants to pay for it. Nobody wants to pay for production in that. And it's also extremely difficult to build. And what's happening is the transistor performance energy improvements we're getting from node to node have really gone down. We're not seeing anything like we saw before. And what's worse is the cost per transistor looks like it might increase. So we might be sort of in the era of these are the cheapest transistors we're ever going to have. If you want smaller transistors, we can build them, but they cost you more each. Right? That's basically, to me, the end of Moore's Law. Right? Moore's Law is really about the cost of the components. So by 2020, Moore's Law will be over, I predict. No more scaling. And this is really, I'm talking about logic, SRAM, DRAM. You know, maybe some of the new technologies, 3D Flash or MVM, provide a different way of scaling. But basically, for the logic, it's kind of game over. And what's really unnerving is there is no successor device out there to the CMOS transistor that's anywhere near competitive or likely to be for the next 20, 30 years, right? If you look at current-day CMOS, you can build billions of transistors on a chip. You can reliably interconnect them with wires, and you can clock it at a few gigahertz, and you can sell it for a few dollars. There's nothing out there anywhere close to that level of maturity to replace CMOS. So this is flatlining, right? This, you know, the next 28 nanometer, 14 nanometer, that's probably what we're going to live with for a very long time in terms of system capability at the transistor level. So that's, as an architect, that's both scary and very exciting, because what it means is all the innovation has to happen above the transistor level. We can no longer just rely on the process guys to carry all the sloppy software along and all the bad architectural decisions we made. You know, just the better transistors make everything better every year. That's not happening anymore. So the efficiency improvements are going to happen above the transistor level. Okay, so the old conventional wisdom about warehouse scale computing hardware is just build it from off-the-shelf components. Maybe you'll design a new board, but basically take the processors everybody else is building, the switch chips they're using, put those together to build a system. The new conventional wisdom, this is Dave's hot rod, by the way, is you're going to build custom chips for this warehouse scale computer. And you're going to engineer this to support the way you want to run this warehouse scale computer. You're going to support SOAs, you're going to support the security, tail tolerance, detection, recovery, prediction of faults in your system. And so you can be building quite different systems than what you could build now with the off-the-shelf chips from Intel and others, right? So custom hardware design is going to be the new reality. And if you've been following the job listings at various large data center companies, you'll see that large upswing in the amount of hardware engineers they're trying to hire, right? And I see this as prevalent across the industry. Much more interest in custom hardware across the industry. So why is this? Well, we covered this. If transistor scaling is stopped, all the improvements in system capability have to come above the transistor level. You're going to need more specialized hardware if you want to do more. And it seems that people want to do more with their computers than they do right now. Another thing is these warehouse scale computers are proliferating. And if you're blowing $100 million a pop on one of these warehouse scale computers, and you're building several of these, it might be worth your while investing in chips that make those systems be able to perform better, consume less energy. Right? So this is the economic argument, might be why you want to do this. Now, the good news in all of this is that once Moore's Law scaling stops, it gives time for the industry, the design industry, to catch up. So there's several reasons why custom chip development is so expensive. One is you're so scared of getting it wrong because it costs so much to fabricate chips, the prototypes. Why does it cost so much? Because technology's been moving so fast that you only have 18 months or 2 years to amortize the cost of building all the equipment you need to do that fabrication. If we stuck at the same node for 10 years, you'll have a much longer period of which to amortize that machinery. Also, all the people developing the libraries you rely on to build the chips, the memory compilers, the pad frames, the standard cells, those libraries will mature and will also be cheaper because they can amortize the cost over more designs. And finally, what we're seeing is an upswing in hardware design productivity. The hardware design is a very difficult job, and they've been working to improve their productivity. And so some of the work that's been going on in academia also, we're coming up with more productive ways of designing hardware. So at Stanford, there's a project called Genesis. So you generate an entire chip and just parameterize that. You can actually build a module that can build instances of chips. And at Berkeley, we've been developing a new language called Chisel based on Scala that simply lets you write these large-scale parameterized chip generators. So there's some hope that we're going to need to do custom chips if we want more capability. And the cost may go down, and it may become easier to do that development with the things that are going on in design tools. OK, so for fun, I thought I'd throw in one of the hot topics in current warehouse scale design, ARM versus x86. Right? This is which ISA should I use? I'm an architect, so people often ask me about this. So, second, third generation warehouse scale computer design, you hear a lot of, should it be ARM, should it be x86? What are the relative merits? Well, if I look at this, the real important differences are nothing really to do with the ISA. They're really to do with the quality of the available implementations. What do the Intel chips look like? What do the available ARM chips look like? That's really what people are comparing. Nothing to do with the ISA. The other thing people compare is the business model. So Intel is not a foundry. You cannot go to Intel and ask them to build a custom chip using their cores. They don't do that. ARM, however, licenses their IP, and a fabless semiconductor company can build custom designs around that ARM core. That's part of the interest why in ARM cores you're seeing in the server space, because there is an existing industry to build custom chips around those cores. My own belief is most of the reason people are interested in ARM right now is that they want to make Intel sell their chips for less, right? Intel makes a huge margin on their server chips. It's basically what keeps Intel afloat. And many other players in the market would like to see that margin go down. But then let's talk about this ISA a little. What's in an ISA, instruction set architecture? It's the most important interface in the computing system. It's how hardware talks to software. And what makes an ISA long-lived legacy is that developers develop for it. So a lot of tools and software get developed from one of these ISAs. But these are third-party. The legacy stuff is not stuff developed by Intel or ARM. It's all the code developed by everybody else using those ISAs. So that investment is made by everybody except the companies promoting those ISAs. So in an open computing future, why do we have proprietary ISA standards? It's just an interface, right? So why is the whole community building their software and systems around this proprietary ISA and having these debates about should it be ARM or x86, because they're the only games in town, right? And why do I have to deal with the business models of these various companies? Is it because x86 and ARMv8 are innovative interface designs? Is that why we're using them? No, right? I don't think anybody would say that, right? ARMv8 looks a lot like 1980s era RISC chip, right? So my belief is the ISA should be an open industry standard. It should not be controlled by a company. It's just an interface. Companies can compete on the execution of implementations. Software developers can target that standard. And there's no real reason to stick with a single company here. So Berkeley, we proposed one. We've actually built one. RISC-V is what we call it, and it's a very simple RISC ISA, but it's been designed to be extensible and customizable as the basis of some of the chips we're going to be doing. It doesn't have to be RISC-V, but I believe that this has to happen, that industry moves to an open standard ISA. There's no reason the most important interface in computing should be owned by a single company and led by those, right? And particularly if you look at the history of open source and warehouse scale computers, the first generation leveraged open source software, the LAMP stack, to build systems and services. The second generation, you're seeing this push to try and build open source hardware, but this is really like open compute. This is really board designs based around existing commercial chips. So what I'm imagining is what we think is going to happen in the third generation. Why don't we have open source chip designs? Why don't we open source how you put together the structure of one of these SoCs going to live in this warehouse scale computer to make it much easier for individual companies to come along, organizations to come along, and customize it for their particular needs, their particular application set. Make it easy to become vertically integrated at the warehouse scale. And so, for example, we're going to plan to release our FireBox. We're actually going to be building chips and building systems. We're going to release our warehouse scale chip generator, free OpenBSD for people to go use to build future chips. Okay, so I've talked a lot about the sort of trends and challenges in warehouse scale computing that we've been sort of surveying and thinking about. Now I want to talk a little about our particular stance on this and our particular stake in the sand, what we view the future warehouse scale computer to look like. So I'll give you a quick overview of FireBox and what we're thinking. So in a FireBox, 1,000 sockets, not 2 sockets in a server, 1,000 sockets. These are individual SoCs which have high bandwidth memory attached. So each socket has the logic chip plus associated high bandwidth DRAM right close on an interposer next to the SoC. So 100,000 cores roughly in one of these boxes. 100 petabytes of non-volatile memory spread over 1,000 memory modules. Okay, so each memory module is sort of 100 terabytes. How is this all connected? Well, there's been a lot of advance in silicon photonics, integrated silicon photonics. I've been working with a group at MIT working on this. It's very exciting. We can basically have much, much greater bandwidth density using photonics than we could with electronics, and somewhat better energy efficiency also. So we're going to connect all these components using terabit per second optical fibers with a huge honking switch in the middle that connects everything. A very high radix photonic switch. So the SoCs talk directly to these bulk NVM modules. And then it connects out to the rest of the data center off to the side. So this switch in the middle, it's not just really a single switch. It's a, it's built up of many high radix components. So there's many paths through this high radix switch, very high bandwidth. So we're hoping to design, make the network kind of invisible to software by making it really high performance, using photonics as the drive in here. So our big bets in FireBox, first of all, why is it so big? Well, we want to reduce operational expenditure, the management costs of running a warehouse. So instead of managing units of 2, 4 servers, we want to be managing 1,000 sockets at a time as a box. We want to support huge in-memory databases directly. Build a system that's designed to do that. The current systems are not designed to do that. Current systems, you distribute the memory across all the nodes, and you have to send messages, and software gets in the way. You really want a big, large in-memory database you can access directly and quickly. Massive network bandwidth, as I mentioned, to simplify the software model. We want to go and rethink the whole way that software talks to the network. Right? There's no reason you're poking registers over PCIe to talk to some device driver to get something done. Modern processors are terrible at talking to I/O. We lather things on top to try and help with that, but really, we want to bring the network interface right into the core, make it very low overhead for software to send and receive messages. So re-engineer that whole network stack and redesign the core to make that possible. And this is what we want to have for low overhead messaging to improve tail tolerance, and also to give as much low latency, high bandwidth access to this bulk memory we're providing. Obviously, we've talked about this already. Data must always be encrypted. Whenever it's on a fiber or in that NVM, it has to be encrypted. So that's happening on the SoC. The only place you operate in the clear is inside this package, which we hope we can make tamper-proof. We build custom chips to support all this. And we do this with an open source hardware generator. We'll be giving away our design to everybody. So you can take a look to see how we did it. And hopefully, this will help the community build an understanding of how to build these systems. Sorry. So I'll talk a little about these photonic switches. It's one of the center points of our design. So I've been working with a group at MIT building this monolithically integrated technology. So basically down a fiber, the great thing about fiber is you can send different colors of light. So we use a wavelength division multiplexing scheme, WDM, and we're sort of working towards a system where you have 32 wavelengths of light, each carrying 32 gigabits a second communication bandwidth. And what's nice is you can send light in both directions simultaneously. Doesn't interfere. So you get a terabit in each direction on a single fiber that you can attach to a chip with a 100 micron squared pad. So that's a radical change in the bandwidth density that's possible over electrical signaling. And also there are improvements in energy per bit. And also it's pretty distance insensitive. So when you're talking about one of our boxes, which is roughly the size of, say, 3 racks, conventional racks, the distance between components is much less important. So the way that the switch chips are arranged, we have a bank of these switch chips in the middle, and the whole system, basically there's only 2 photonic hops from any socket to any other socket. You can view the box as containing 2,000 sockets that you can populate with compute or NVM modules, any configuration you see fit. But from any component to any other component, there's 1 hop to a photonic switch. There's another hop back to the destination. Right? So very rapid communication across the whole system. And multiple paths as well. So there's a lot of redundancy in how you can communicate through these switches. So there's many available pathways through these chips. The chips can fail, and so on. So very fast, low latency switch. That's one of the key things that really simplifies the whole system design. OK, so we provided this fast network. How do we manage programming this whole box, 1,000 sockets? So as an architect, it's interesting to go back at looking at arguments 20 years ago when we started building big multiprocessors. How should people program big multiprocessors as we scale them up to more than a few sockets? Well, the old conventional wisdom was, well, shared memory. Because this really simplifies programming. You don't have to figure out ahead of time what data you need to send. You can just send pointers, and the receiving end control through the data structure to find the pieces. But really, what we see is pretty clear is message passing kind of won this war about how you program a large server, especially at this scale, 1,000 sockets. It's much more predictable than wide-scale coherent cache memory. The conditions, what happens when things go wrong, is much easier to reason about if you have message passing. It's a great match to the service-oriented architecture. Also, it provides a uniform way of communicating between components, whether they're in the same box, in the same data center, in a different data center, across a different continent. You still use message passing between those components. So the way the components are going to communicate is basically going to be message passing. They really won the war here, going back 20 years ago to the original big machines like Origins and things like that. So fast support for messaging will be important in these systems. So just diving down into what we imagine being on one of these chips, something like 100 homogeneous cores, maybe less, maybe more, depending how brawny or wimpy you want to make those cores. And the reason we believe these will be homogeneous, it'll really simplify resource management in the system. You don't want to have to care about which core you're mapping to. But we do care about specialization, as I mentioned, to get better efficiency. But the way we see specialization coming into these systems is with a suite of accelerators around each core that really are modeled more like vector units than they are like discrete GPUs. So the notion is each core is carrying with it acceleration machinery of a standard kind. And what increasingly I see is people first go down the path of trying to do custom hardware. They eventually realize, oh, a vector unit is actually the right thing for my application, right? People make this path. They do FPGAs, do custom chips. For a lot of applications that people are interested in, for example, machine learning, crunching images, video, vector unit is really the right thing to do. And that's good because we know how to program that and build that in. So you're going to see much wider vector units in these future systems. And you're going to see extra types of specialization. That's one thing we're working on top of that vector unit to support more different kinds of computation than straightforward data parallel. So the accelerators and specialization around each core, and the cores are homogeneous. This is a much simpler software model. So you can operate directly on data in place. You don't have to ship it to some accelerator somewhere. Of course, we use our RISC-V instruction set. Within a chip, it'll be cache coherent. It's easy to maintain coherence on a single chip. That simplifies the OS management of that chip using many threaded components. Compress encrypt engines, we're going to need that to support the high bandwidth and keeping everything encrypted all the time. And implement the whole thing as a parameterized chip generator, so you can retain the same template, but modify it to add your own secret source in there, while retaining the same software model, same OSs and everything, and most of the same design. Let's talk about storage. So what are we imagining in this NVM module? So what we're saying is each module, one of these 1,000 modules in a given configuration, 100 terabytes of NVM. So how is that possible? Well, it's really only 1,000 chips with a terabit per chip. We're already at 120 gigabits a chip in Flash. So with these new technologies, a few more doublings, we should get to a terabit per chip. We can stack these. So it's only 32 stacks with 32 chips per stack. That's not outrageous by 2020. And what we're imagining inside this module is building the photonic I/O into the base chips in those stacks. So now with this many chips inside one of these modules, you have a credible amount of parallelism to help with performance, but also a lot of redundancy to help with failure. And what we see is that there are actually good opportunities here. If you have a very fast network containing a lot of memory, connecting a lot of memory, this may help provide greater availability also. If I detect a fault, an error in some data, one copy of the data, I can quickly reconstruct a new replica by quickly fanning out data from all the other copies to create that new one. So maybe if we reserve enough bandwidth in the background, we can provide this continuous availability in this large-scale NVM. We're going to need it. At 100 petabytes is going to be a lot of failures. But with enough bandwidth and with enough parallelism inside each module, there's a lot of redundancy and capability to, on the fly, be rebuilding this stuff without affecting the performance of the foreground applications, right? So good area of research is how do we maintain all these replicas? How do we keep things going all the time and taking advantage of this massive network bandwidth and the huge amount of parallelism from the very large number of solid-state chips we're going to have in these massive data stores. So quickly, some of the more larger scale highlights. So we're imagining, maybe 8 to 32 DRAM chips, so up to 128 gigs of RAM on each node, maybe 500 gigabytes a second or more of DRAM bandwidth on that in the socket. Message passing, we'll actually have the actual message maybe at the instruction level and throw exceptions, so you can quickly handle faults in messaging. And across the system, maybe only add 100 nanoseconds to talk to anywhere across the whole system. So really sort of a couple times DRAM latency. Lots of error detection. Excuse me. No disks in the standard box. Disks are out in separate boxes, providing cold storage. Around 50 kilowatts for a box. As I mentioned before, roughly, we're imagining something about the size of 3 standard racks. So we divide that power budget between sort of 35 kilowatts for the sockets, broken down as you see, and 15 kilowatts for the bulk memory and crossbar switch. Okay, so there's a whole bunch of issues this raises. This is a new machine design. You know, if this was to be the design in the future, what kind of questions? Well, how are you going to improve tail latency and maintain high utilization? You know, some of the techniques are things like partitioning in the hardware. Maybe there's some other techniques we can use. How are we going to bridge the inbox protocol out to regular TCP/IP? And where do we do that bridging? Do you connect fireboxes together using this messaging, or do you go back to IP to communicate? Where does that bridging happen, and how does it happen? How do we connect to RPC? Is it really new ISA instructions? Is it an API? How should that be handled? What's the role of virtualization here? Are we going to be virtualizing whole boxes, or maybe the right unit of virtualization is actually the service? So maybe the service is the unit that you want to virtualize, where a service includes data storage, the compute required, the network addressing. So instead of addressing an IP address, maybe I should be addressing a service, and that should be the addressing that's used by the network. And it's easy to move services around. So we've said we're going to keep everything encrypted. So a big challenge here is if you have to keep everything encrypted in the non-volatile memory, how are you going to do all these operations? You cannot do a lot of most kinds of processing near the memory. You have to bring it to the socket to operate on it. Is that actually plausibly tractable? Or are there things we can do? Can we keep it encrypted and do some simple operations out in the NVM? How are we going to manage this? This is a big open question. But I think the demand is definitely there to keep everything encrypted all the time. So how much failure area recovery, prediction recovery? And where do we place the smarts for doing this? In the cores, in the hardware units, in the software? Where do we place all these mechanisms? I think a big challenge for the attendees here is, say you have 100 petabytes of non-volatile memory inside a box. How are you going to securely manage this, given that this is storing data from many organizations in the cloud? Right? So how are we going to keep this safe and secure and make sure people can't see each other's data? And how are you just going to manage it? Sometimes it's going to be used more like a file system. Sometimes it's going to be used more like memory. What's the real structures you need to manage that huge pool of memory? Another big question for us is, anybody want to help us? So we're going to be trying to build this thing, and we're looking for help from industry to help us with constructing these FireBox prototypes. Okay, a lot of questions for FireBox. How are we going to go about answering these questions? We could just build a few and see what happens, but we probably need to do some simulations first as good architects. But what we want to simulate is a very, very big system running very big applications. How are we going to do that? Well, at Berkeley, we've been working on FPGA-based acceleration for a while now. Recently, we've had some success getting a whole data center simulation up. So we call this project Diablo. And Diablo stands for Data Center in a Box at Low Cost. And the idea here is to build a wind tunnel for future data center designs. So the idea is to model sort of order 10,000 nodes and the accompanying 1,000 or so switches, and to run them in simulation for around 100 seconds, a couple minutes. That's enough simulation time to get a good feel of what's going on. And in this simulation, we're going to be running every instruction in the whole software stack and seeing every byte and every packet move through the network. So this is not an abstracted simulation, but actually execution-driven simulation of data center at this scale. So we built this. Student Zhang Jitan was responsible for this. He recently graduated. This is our Diablo Run prototype. It's a stack of FPGA boards, total of 24 circa 2007 era FPGAs. These are very old FPGAs. But on this stack of boards, the capacity, we can actually simulate up to 3,000 servers in 100 racks with about 100 simulated switches, and running at about 8 billion instructions per second. Right, so actually modeling all of this execution-driven. To give you an idea how we do this, how do we map the data center for FPGAs? The important thing to realize is we are not taking the hardware design of a warehouse scale computer and mapping that to an FPGA. What we're doing is designing a simulator and accelerating it using FPGAs. So we're using FPGAs to accelerate a software simulator. We are not just building an FPGA computer that matches a warehouse scale computer. It's an FPGA accelerated simulation. And so we build functional models, timing models. We map those to hardware pipelines on the FPGAs. and use a lot of hardware design techniques like hardware threading of those models to get good efficiency. And so the whole design basically boils down to two kinds of FPGA designs, one that models a rack of servers plus the top of rack switch, and another one that models just switches, data center switches. And in these models, we can change a lot of parameters without resynthesizing the FPGA. They're just parameters to change the simulation. So to give you some idea of the things we can do, we sort of took a look at, well, what do other people do for simulation in network design? So this project was primarily interested, how are we going to build this network? What should we put in the network? Well, if you look at recent SIGCOMM papers, when the x-axis here is number of servers in the simulation, the y-axis is number of switches, you can see they're all clustered down to the bottom with one outlier, which was Microsoft. We spent a lot of money building a big prototype system. What's interesting is one of the systems here used 0 servers because they just modeled the traffic abstractly. They didn't actually model anything happening on the server. So what can we do with Diablo? Well, so the median is pretty small. So what can we do with Diablo? Well, first thing we have to do to show Diablo is to change the scale of the graph. So push everybody down the corner. And with Diablo, we're kind of modeling, 3,000 servers or 100 switches all at once. So what does this let us do? Well, it actually lets us look at these effects that we're trying to get at in the warehouse scale computer. So in particular, we sort of reproduced this latency tail figure that Luis Barroso presented at his FCRC keynote a while ago. And what's showing here is the x-axis is latency of a request coming back from Mcached, and the y-axis is the frequency, so we're showing the histogram. And you can clearly see in here the effect of whether the two ends are in the same rack or in different rack and going through multiple levels of switch. Those are the different humps in this latency peak. So we can clearly see that in our simulations. And what's more, we can do experiments. Like, let's try a better interconnect. So we tried just upping the rate of the interconnect to 10 gigabit from 1 gigabit. And we saw that, yes, that helps a bit. You kind of roughly, but you only roughly half the latency. And why is that? Well, the problem isn't actually the network. It's the software stack. So what we found is we can improve the hardware and the network switches, but the reason this system is bottlenecked is because of the software stack. So let's improve the software stack. So on our system, we can go change the version of Linux we're using and improve the tail. So we can actually see this. So on a simulator, we just, change those 2,000 nodes to run a new version of Linux kernel. So instead of running, remember this 2.6, we now went to 3.5, and we saw the tail move up into the right, which is up into the left, which is good. So we can actually see the effects of software because we're modeling the processor cores, we're modeling the network interfaces, as well as the network in great detail. So, all those people who are not looking at what's happening in the software are missing what's happening in this warehouse scale computer. So modeling things at this scale is how we imagine making these design decisions in FireBox. And so we're working on a FollowOn system, Diablo 2. Diablo 1 used 2007 era FPGAs. A new system, we hopefully use newer FPGAs and a lot more memory and a lot more flash to model future fireboxes. So that's kind of how we imagine making progress in this. And we're looking for help with actually building Diablo 2, and also looking for people who might be interested in getting copies of this system once we bring it up. Okay, so I want to wrap up to leave some time for questions. So one thing, FireBox, where does the name come from? Well, it's the place you shove the coals in a steam engine to keep it going. And in our processor development, we use locomotives as the name of our different processors. So that's why we call this FireBox. So FireBox is our idea for what the 2020 warehouse scale server would be. Where do you want to raise the abstraction level for programmers, get rid of a lot of the awkwardness of current systems by customizing the hardware to them, making use of new technology, optical fiber, solid-state store. And it's really a kind of supercomputer if you think about it. We're building a big box, which is a supercomputer, but a particular kind of supercomputer. It's designed for interactive and batch applications. It's multi-programmed, many different users. It needs to be available 24/7, and needs to be fault-tolerant and tail-tolerant. So a new kind of supercomputer is what we're building. And as I mentioned, we're looking for help. So I'd be interested in talking to industry people who might want to help us with this project. So I also want to acknowledge this is not just me and Dave, but a whole team of people at Berkeley and outside who've been helping us with this project so far. Okay, so I'm done. I'm happy to take any questions.
Hi, this is Rick Ferro. So first thing that occurred to me as you were talking is the maintainability. I mean, one of the reasons why Google, Amazon, Yahoo, they all go with these simple services. One, they were cheap, and two, one breaks, once they determine it's really broken, they just send in somebody who's not very well paid, slide it out, slide in a new one, reconfigure it, and it goes. So now you're talking about putting 1,000 nodes in 3 racks. Of course, at first I was really imagining a firebox, so with things very densely packed and there's no way to get anything out. So I see this as probably a barrier. Have you thought about, you know, physical maintainability, being able to replace nodes, being able to replace your photonic switches, your network fabric?
Yes. I mean, you pull out just as you do now, you pull out a component, plug it back in again.
So it really does look like several racks is what you're expecting.
Physically, yeah. Well, the reason we chose box as opposed to rack is because of the connotations that rack has in most people's mind.
Sure.
And we do think a bigger unit than a standard rack is important and possible with the interconnect. But yeah, the idea is modules should be replaced. But you want to be able to hot swap the NVM modules. You know, when they wear out, you want to put a new one and keep the application shouldn't even need to know that happened. One thing that optics does make a lot easier is there's many fewer connections in the system. You know, there's not these big wide fat connectors. There's many fewer connections at any point in the system. So it does make it easier to hot swap.
Okay.
Yeah, but definitely, it's a good point. And yes, for sure.
Well, the second question was, why Linux? Shouldn't there just be some other form of really tiny operating system that just exposes an API that's expected? There was work at Federated Week. It's been done by a couple of Microsoft researchers, where they essentially create a kind of virtual environment which has you know, a dozen system calls that can run most applications that already exist.
Right, I think I completely agree. So we put Linux up because if we don't, people say, why don't you have Linux? But I completely agree that, and actually one of the things we're looking at is maybe the software container I want to build is something that runs a service. So that's why I talked about virtualization. The unit of virtualization should be a service. And inside that bubble, a partition of resources, you place enough runtime to run that service and nothing else. Yeah, I completely agree. But if we didn't say Linux, people would say, why not Linux? So.
Sure, I understand. Okay, thank you.
Hi, Ted Wong, Illumina. So why hot pluggable? Why not just make individual units be fail in place? You know, if it doesn't work, let it die. And once you get to a certain scale, you know, the chances are you send someone in to repair one of these things or replace something, they're more likely to mess up something that's working than fix something that's not.
Yeah, that's an argument that's orthogonal to the FireBox design. There's nothing, you could go either way depending on your preferences or how much you expect these things to cost and the failure modes. So sure, that's a fine issue to debate. I think it's kind of orthogonal to this particular architecture.
All right, thank you.
Okay, Kim?
Kim Keaton, HP Labs. So you mentioned that we're going to see increasing specialization in the computational devices that we have at our disposal. If everyone's going to be doing customized processors, who's everybody in that statement? I mean, is it every service, every cloud service provider? Is it, you know, every handful of manufacturers that are going to be providing a handful of alternatives? Is it, you know, everyone who wants to write their own application? Can you say a little bit more about that?
I think, yeah, it'll be interesting to see how this market shakes out. I do know that the few very large providers are working on custom chips, not because they've told me. I don't know anything about what they're doing privately, but just from looking at job listings and the interest people have in certain parts of our project versus others. So at least the big providers will be doing this. I think what's exciting is if we move to the more open source model, there'll be more hardware innovation from possibly startups, which is kind of really atrophied in the valley right now, who may propose alternative boxes for certain purposes. And it'll make it easier, hopefully, for smaller players to come in and offer new and different kinds of box based around maybe the same infrastructure. The idea would be that as well as the chip generator letting you build different kinds of chips, they would retain the same programming model. So you wouldn't be rewriting all your software for this different box. It would look the same, just with some extra, you know, secret widget, special widget that's custom for a given application domain. So the hope is that it shouldn't just be the big guys who do this. There may be opportunity for all kinds of innovative new kinds of box that people come up with.
Well, it seems like there's all sorts of questions about how portable code will be from one, you know, set of chips to another. Also, how much heterogeneity there's going to be within a given environment.
So yeah, talking about the portability, I think what's important to realize is probably 99.99% of code doesn't need to touch an accelerator. But the 0.01% that does, it's okay to retune that for a different box. If your whole software environment looks identical, there's just a few kernels you're changing. So that would be my vision. And as for the standardization, we think there should be an open industry standard for the ISA, which would, and all the software should be developed for that ISA. And most of the software, like I said, is going to be standard kind of code that shouldn't change as you move to accelerators. It'll only be very key kernels, small pieces of code. And the thing to realize, people rewrite these big services regularly because scale is increasing and demands are new. So there is a continual churn in software in these systems. And as long as you can keep all the legacy stuff running and inject the new widgets, I think that's the path for adoption, I think. Yes.
Serge Pashenkov, VMware. You said at the beginning that the disk is new tape, but then the disk kind of disappeared from your pictures. So
Sorry, say again?
at the beginning you said that the disk is a new tape, but then in the design pictures that you showed after that, there is no disk at all. So do you see it? Do you think about it? And very specifically, if it is a new tape, tape has an advantage of not consuming power sitting on the shelf, and disk is different. So specifically from that angle.
Okay, yeah, so in our project, we're trying to constrain what we do. We're being ambitious already. So for example, we're not considering management of those disks. We believe they exist. Some people are advocates of tape continuing to exist. Dave in particular is very strongly against that, but I'm agnostic. But that's outside the purview of what we want to work on. Another thing we're not looking at is, specifically, is the data center level network between these boxes. That's a very interesting, active research area. It's just one we're not choosing to focus on. So it's really not that we have got rid of the disk, we're just not actively going to be working on that in this project. We're concentrating on the solid state box for this project.
I'm Umesh Maheshwari from Nimble Storage. I have a similar question at a different level. So you suggested that DRAM might be replaced with NVMs. And I was wondering why that might happen. One possibility is that because NVMs generate less heat, they can be packed more tightly, so you can have much more of them. But the other possibility, which might be more exciting, is that with that, applications don't have to be bifurcated in their view of volatile memory and persistent storage. So do you think that would be a driving factor? And if so, so lots of applications will need to be rewritten. So how would that happen?
So let me just try and answer the first question. So I think the reason we don't see DRAM going away, we see DRAM becoming this high bandwidth layer on the package. The reason NVM will replace the bulk memory if we have a successor to flash is because the cost per bit will be so much lower and it'll be non-volatile. There'll also be power advantages, but the primary reason will be just the cost per bit of that bulk storage. You can access at rapid rates. That's going to be why the NVM will displace DRAM in that bulk memory capacity to provide that capability. Now, if there isn't a successor to 3D flash, I think you'll still see bulk DRAM along with bulk flash, just because flash is too slow and doesn't have enough endurance. So I think plan B for us would be that the bulk memory is actually a combination of DRAM plus flash if a new NVM doesn't come along.
I see. Okay, thank you.
Let's take one last question over there.
Thomas Fenning from Microsoft. You made some repeated comments around that all the data getting in and out should be encrypted. That's sort of a desirable goal by in itself, but when you really start thinking about it, then you realize that protecting the keys and the crypto engines is sort of getting very critical there, because you need to figure out what you want to protect from. Could you comment a little bit more what you have in mind there and what the mechanisms are that you're planning at the chip level to actually do that?
Yeah, so I think there's been a lot of work in making packages tamper-proof, so you can't physically get at the keys, and then having some kind of physical function on the key to identify it. So you're going to have to trust somebody, and you're going to be trusting that hardware provider. And that might be a scary thing to do if the hardware provider is also the software provider. So it is going to be difficult for software. This is an active area. How do we build that trust in the hardware inside there? I think actually the encryption, even if it's not 100% infallible, will be a necessary checkbox to have in your data center, because no CIO will put it there if you don't have it, even if it could be theoretically broken by somebody, right? So I think this is going to happen in fits and starts. And it's a big active area. It's a difficult problem. I agree.
Well, I would like to thank our speaker one more time for an excellent keynote.